Okay, so I'm back in TEM mode or GIF imaging mode, and this is the region of the sample that I'm currently looking at. So there's silicon and silicon oxide in this region. So I'm going to focus initially on the silicon edges, so probably the silicon K edge. So okay, so we want to do some eels, so we need to be in the spectroscopy technique. I'm already in the spectroscopy technique. Spectroscopy. And I need to change the filter to eels mode. So we go over to the microscope UI, go back to eels mode. So we're running at 0.75 eV per channel dispersion. We're going to go into dispersion a little later. And the energy offset's 300. Always we want to see what the zero loss peak looks like. So let's go back to 0 EV, single eels, and start in HQ mode. Remember our kind of base conditions, and shortest exposure 0.1 microseconds. So I'll start my eels view. Use auto exposure to increase the view time. The tuning manager state is green, and the full width half maximum looks pretty good. It looks like a fairly sharp zero loss peak. It's not quite at 0, so I'm going to hit align ZLP, and there we go. Okay, so I want to kind of focus on the K edge of silicon. So I want the zero loss peak to be out of the field of view and the silicon K edge to be in the field of view. So let's use the periodic table, choose silicon, and see kind of what field of view we have. That's a little excessive, so let's go down instead to, say, 1,000. Yeah, maybe a bit. Yeah, that's probably good enough. Okay, so we don't really have anything much signal, so I'm going to use auto exposure again. There we go. Okay, so now we can see the K edge. So the view time auto exposure is chosen 0.65 seconds. And I'm going to stop the view. So it doesn't look too bad at first impression. We can have a fairly clean background, and we can see the edge that we're interested in. But just recall the conditions that we have here. So at the moment, the objective aperture is not inserted. So there's no objective aperture, which means the collection angle is greater than 31 milliradians. So it's pretty big. I'm going to put the objective aperture in, which will limit the collection angle to 15 milliradians, 15.36 milliradians. So let's insert that 60 micron objective aperture. And we'll do the exact same thing again. I've turned off the auto exposure. The dispersion is the same. In fact, I'm going to copy this one. So Control C, and then Control Alt V. And then I like to rename things as I'm going along. So I press Control D to bring up the image info. And then I go to the info part, info tag group. And then we're going to say silicon K, 0.75 EV per channel. And OA none. We also might want to rename the slice. This is the image name, not the slice name. So we can go to line plot and change the name of spectrum to be silicon K. And I'm going to call that OA none. And then hit update. that's kind of useful if you want to copy and paste line plot data onto other line plots, because then the naming is carried through into the slices, which is quite handy, and it's easy to keep track of what's going on. So that's our no objective aperture state. So I've just, objective aperture is now inserted. Let's do exactly the same thing again. It's the same dispersion, same energy offset, same view time, just the aperture. So view. Okay, so we've got less absolute signal, but you can already kind of see that the jump ratio is different. So a nice way to compare those again. So I'm going to stop the view, rename this one. Well, let's copy it to a new one because that's the view. So let's copy to a new image object, rename. What did I call the other one? SIK 0.75 EV per channel, OA 60 micron. OA 60 micron. Okay, so I'm just going to copy and paste. So Control C and Control V. So I'm going to paste the 60 micron aperture data on top of the no aperture data. So so we've got less signal. That makes sense. But let's have a little look at the jump ratio. So the way we can make a nice comparison, there's a normalization feature. So I'm going to draw a rectangular ROI on the line plot. If you right click over in the kind of the white space to the right hand side, and then go to the display menu or sub menu, and then hit show legend. Now I can select these. So I left click on the legend entry for Silicon K OA none, hold down the shift key on the keyboard, do the same thing with the other spectrum, right click, go to align slice vertically by, and I'm going to choose integral, and that's going to normalize the integral of those two spectra over that region. So then you can really see the difference. So look at the jump ratio when we have when we kind of have a smaller collection angle. The jump ratio for this and this new spectrum is huge compared to the other one. And that's because we're really helping ourselves in terms of signal to background ratio. So remember the points in the lectures about the characteristic scattering angles, and that we want to kind of tailor our collection angle to the characteristic scattering angle for a particular edge. So if we have a little look at the notes that I wrote down, so the characteristic scattering angle for the Silicon K edge, well, I've actually modified these notes. So the characteristic scattering angle for Silicon K is 5.3 milliradians. And remember, our rule of thumb is that we want to have a collection angle that's around 3 times the characteristic scattering angle. So that would make our kind of ideal angle for this ionization edge 16 milliradians if the numbers are perfect. So the collection angle for the 60 micron aperture is 15 approximate milliradians. So by using this aperture, we're really optimizing the collection angle for this ionization edge, and that's why we see this kind of drastic change in our jump ratio and our kind of signal to noise ratio, signal to background ratio. Okay, so that's hopefully illustrated why it's important to know your scattering angles, know your collection angles, how to measure them, and kind of, which conditions to choose in terms of apertures.